Yeah, well, first of all, thank you very much to the organizers for setting up this 26th instance of QIP in this absolutely gorgeous city. I'm really excited and looking forward to a whole week of interesting talks and exciting discussions, hopefully. So it's a pleasure to kick it off, telling you about topology, supersymmetry, and quantum computing, and how these three things interrelate to one another, and they come together to prove the main statement in the title. This is work which was done in collaboration with Tamara Kohler, who's a superb collaborator, currently in Madrid and moving to Stanford for a postdoc in the fall. So if there's anything that I would like you to remember about this talk is the slogan that homology is quantum mechanical. That's what I want you to remember from the talk, hopefully also what that means, not just the words. So just to give a little bit of context, the week before the QIP submission deadline this year was a little bit of frenetic submission, and there were a couple papers appearing on the archive that you may have noticed, all with the title on topological data analysis and homology. So there were these three papers, and then ours, and then another paper by Seth Lloyd and Sasha Schmidholder. And if you were not aware, if you're not following the archive, this actually even made it to Twitter, where it was accurately depicted what happened that week. So the goal of my talk is to give you a little bit of context of what all these works are about and what the excitement is about. So the first three works mostly deal with algorithmic aspects of the so-called problem of homology as applied to topological data analysis, and the two papers in the bottom deal with complexity aspects of the problem. Okay, so a little bit of advertisement for my colleagues. There's going to be a little more of topological data analysis at QIP. In particular, two of those papers that I mentioned earlier will be presented on Friday in Vedra and Junko's talk at 1:30 p.m. in Auditorium 2, if the schedule hasn't changed. And following that talk, a talk by Gillian, also on algorithmic aspects of TDA. All right, so let me tell you about the homology problem. So the homology problem is a basic problem in computational topology, which is, roughly speaking, formulated as follows. So you're giving us an input, a simplicial complex. So I'm not going to go into details on how the input is provided, in what format, not now, later. But the output is, you're supposed to output the number of k-dimensional holes of the simplicial complex sigma. Okay, so what I mean by a one-dimensional hole is, you see, for example, see if the pointer works, if you can see it. This is a one-dimensional hole in the sense that it's a one-dimensional loop that is surrounding an empty void in the middle. Okay? And similarly, this tetrahedron there, which is, if it's empty inside, that is considered to be a two-dimensional hole. So the terminology can be a little confusing because the dimension of the hole is the dimension of the space surrounding the hole. Okay? All right, so the study of homology really goes back to the beginnings of topology in the 1900s by the hand of Poincaré, and others. So it's a very classic topic in topology. However, the computational problem of homology, as I just formulated, was posed formally, to the best of my knowledge, in 2002, in this very nice collection of problems in computational topology. It's 35 problems, and this was problem 33. So we're going to consider the decision version of the problem, which amounts to asking the question, does a simplicial complex sigma have a k-dimensional hole, yes or no? So this problem, even though it was formulated in 2002, it took a while, 14 years, to prove that it was NP-hard, in this nice work by Adamaszek and Sacco. But a full complexity of a full understanding of the complexity of the problem remained open. So in particular, there was no upper bound given, and the lower bound given by NP can be improved substantially. So given that this is such a fundamental problem, why is it so that the complexity has kind of remained open, or poorly understood? And I want to argue that in part, that is because homology is intrinsically quantum mechanical. And the better place to understand its complexity is by looking into quantum complexity classes. So let me remind you that QMA is the class of problems which can be efficiently checked by a quantum computer in the case of yes instances. And there's a tiny variation of QMA called QMA₁, which I'm going to go into more details later. But these are two quantum mechanical classes. They're defined in terms of quantum computers, and there's a version of the homology problem, which together in a previous work with Chris Cade, who should be here in the audience, we termed the K-local homology problem, and this problem we could show was squeezed in between QMA and QMA₁. Okay, so in this sense, the general problem of homology is captured by sandwiching between these two quantum complexity classes. So this was the general problem, and today I'm going to tell you about a specific instance of this problem called Clique homology, which is relevant to the problem of topological data analysis. Okay, so that is a technical proof, and what I'll go over during the talk is going to be a technical proof, or technical reduction, but it's nice to understand why things are the way they are beyond just the technical proofs. So why is homology quantum mechanical? And it really goes back to a paper by Ed Witten in 1982, one of his many famous papers entitled Supersymmetry and Morse Theory. And it was observed in this paper that there's a special class of quantum mechanical systems that are called supersymmetric systems. And these supersymmetric systems have the interesting property that the ground states of these systems are one-to-one correspondence with elements of homology. Okay, which I'll explain soon exactly what that means. But given this correspondence, that implies that the complexity of homology, of understanding if a certain space has holes or not, is equal to understanding the complexity of finding ground states of these supersymmetric systems. So if you understand one, you understand the other. The thing is, nothing was really known about the complexity of finding ground states of supersymmetric systems until we embarked in this project. So today's main technical result is the title of the talk, that Clique, or something also equivalently called independence homology, is QMA₁-hard. And this is what I'll try to explain what this means and how to prove it. As I said, this is a particular instance of the homology problem which is relevant to TDA. Okay, so to prove this, we're going to need a confluence of several different fields. Of course, topology, in particular simplicial homology. We're also going to need a special class of many-body systems, which are fermionic many-body systems, and they have this special symmetry called supersymmetry, which relates the coefficients of different fermionic terms, like quadratic and quartic, like here. And of course, a definition of QMA₁. So I want to argue, and we'll discuss this hopefully, well, by the end of the talk and hopefully throughout the week, that this is a fertile ground for finding problems with provable quantum advantage beyond the problem that I'll be describing here. Okay, so why are we interested in homology? So as I said, first of all, it's a fundamental problem in topology. So as an academic, that is enough interest, to me at least, but it's also of practical interest as it relates, as I mentioned, to topological data analysis. So in topological data analysis, well, this is a general term to kind of an umbrella that encompasses many tools for extracting the shape of data, or the topology of data. One of the problems that appears in TDA is you give a point cloud of a large number of points in Rn, and you would like to, if you squint a little at that first graph, you see that it has the shape of a circle, and you would like to extract the topology of this data. So this is used, for instance, as a form of dimensionally reducing the data. So you have a large number of points, and you want to extract some basic features of the data such that you can, for example, run machine learning algorithms on that. So a third motivation, in particular for this talk, and as it relates to some of the other works, is that there's a quantum algorithm for approximating homology. So even though homology is hard, very hard, as you'll see, so not even a quantum computer can solve it exactly, there are ways of approximating homology. And it turns out that you can find an additive approximation to some normalized version of the number of holes in a simplicial complex. And you can do this efficiently with a quantum computer, which, as shown by this paper by Lloyd, Gardner, and Zonardi, where they have a quantum algorithm for doing this. Now, as with other machine learning quantum algorithms with applications to machine learning that came around the time, some of them were later dequantized. And so people perhaps started getting increasingly worried that more and more things would get dequantized. However, this algorithm resisted dequantization. Okay? And there's a good reason for that, which is that you can actually show that for the general problem of homology, so we haven't yet proven this for the case of the Clique homology, but for the case of general homology, you can prove that this problem is DQC₁-hard, and therefore cannot be dequantized unless DQC1 is equal to BPP. So to remind you, DQC1 is one quantum complexity class that has to do with having one clean qubit, and it is believed to be strictly bigger than P. So this problem cannot be dequantized unless DQC1 is equal to BPP, and in that sense, you have provable quantum advantage for this problem. Okay, so the plan of the talk is the following. So I'll begin by telling you about simplicial homology, then I'll tell you about supersymmetric many-body systems, then I'll review basic aspects of QMA₁ and quantum KSAT, from which we're going to do our reduction, and then putting those things together, we're going to prove the main statement. Okay, so let's begin with simplicial homology. So the basic building blocks of simplicial complexes are simplices. So a zero simplex is a point, a one simplex is a line, two simplex is a filled-in triangle, a three simplex is a filled-in solid tetrahedron, and so on. You can go up to arbitrary dimension. So a standard notation is to denote the vertices by x sub I, and then you put them in between brackets to denote that it's an oriented simplex. X0 denotes a point, x0, x1 denotes a one simplex, which is oriented in the direction from x0 to x1. And that's what this arrow represents here. Okay. Similarly, x0, x1, x2 are the three vertices of this triangle, and this particular ordering induces an orientation by the right-hand rule of that simplex, and similarly in higher dimensions. So for once in topology, terminology actually makes sense, which is that a simplicial complex is obtained by simplices. So you have simplices and you have complexes. And complexes are obtained by gluing together these simplices according to certain rules. So you have to glue them along faces. You cannot glue them, you cannot just take a vertex in the middle of the face of something else. It has to be attached to something of the same dimension. All right, so that's the basic idea of what the object is. So you can think of simplicial complexes as giving you triangulations or higher dimensional versions of triangulations of spaces. Now, another fundamental object is the so-called boundary operator. So the boundary operator is something that takes as an input a simplex, and it returns the boundary components of that simplex. So for example, here, you give it one simplex as an input, and it returns the output, which is the two vertices at the endpoints. And it returns them in this kind of superposition. This is just a formal sum of the two zero simplices that make the boundary, and this relative minus sign that is put in there kind of by hand is just to remember the orientation of the original simplex, and it's part of the definition why that sign appears there. Then the action, for example, on a two simplex is given by, so you will return the boundary elements of this triangle, which is an alternating sum of the three edges denoted here, and you can think that this minus sign, what it does is you can think of it as reversing the orientation from 1 to 3 to 3 to 1, and you see if you put those together, indeed it gives you the boundary of the triangle, and so on. So there's a more formal definition, but this is operationally how the boundary operator acts. So it has two main properties that follow from these signs that you put there. The first one is that the boundary, so closed loops, things which are literally closed, indeed don't have a boundary in the sense that the boundary operator acting on them annihilates them. So you can see, for example, here, if you act at the boundary of these, of the outer part of a triangle, so this is not filled in, you get the boundary of the first edge plus the boundary of the second plus the boundary of the third, and because of these minus signs, things cancel out and you get 0. And another consequence, which should also be true about anything that has the right to be called a boundary operator, is that the boundary of a boundary vanishes. So you think a little bit about it. Something which is a boundary of a higher dimensional thing cannot itself have a boundary. Otherwise it will not be a boundary. So for example, a circle is a boundary of a disk, but the circle itself doesn't have a boundary. So that means this operator has to square root of 0. Okay, so with those two elements, we can now define more formally what a hole means. So a hole is a sequence of, in this case, a one-dimensional hole will be a sequence of edges, given this linear combination here with a particular orientation, with the following two properties. The first one is that it is closed. so that it encloses some region. So it cannot have a boundary, so it has to be annihilated by the boundary operator. So in linear algebra terms, so that means that this is called a one-chain, something which is a linear combination of one simplices, has to be in the kernel of the operator, has to be annihilated by the boundary operator. And the second important property is that this one chain here should not be the boundary of a higher dimensional chain. So if this triangle were to be filled in, you see that that cycle would not be a boundary because you could just contract it down to 0, okay? And there will be no hole. So in terms of linear algebra, what that means is that this one chain should not be the image of the boundary operator. Okay? It should not be obtained by acting with the boundary operator on a higher dimensional object. So you can similarly define this for, you can think about two-dimensional holes, and it's the same condition. Okay? So this brings us to defining what the notion of homology groups. So first, let's define what a K-chain is. So a K-chain is a linear combination of K simplices with arbitrary coefficients in front. So these coefficients can be taken to be real numbers or rational numbers or integers, depending on whatever you want to do. For us, it's going to be natural to take them to be in the complex numbers because we're doing quantum mechanics. Okay, so you see that if you have a total of n vertices, the maximum number of K simplices that you can have is n choose K. Okay? So a general K chain can contain up to n choose K terms. And then this boundary, so then the homology group, the kth homology group of the boundary operator del is defined to be everything which is in the kernel, so all K chains which are in the kernel of the operator, but not in the image. Okay, so those which are annihilated by del, but are not themselves the del of something. So you see, because del squares to 0, anything which is in the image is also in the kernel. If you can write x as the del of y, then del x is equal to del squared y equals 0. So you can think of this as a coset group. In fact, so both the numerator and denominator are abelian groups, and this coset makes sense as a group. Okay? But this precisely captures the notion of a hole. So things which don't have a boundary, but they are themselves not the boundary, something else. So counting the number of holes or computing these Betty numbers is equivalent to computing the ranks of these abelian groups or the dimensions of these groups, if you think of them as vector spaces. So these are the so-called Betty numbers. So at the end of the day, what this amounts to, if you want to find holes in a simplistic complex, this amounts to doing linear algebra on matrices of size n to the k times n to the k, because this boundary operator just will act on these k chains. So this is going to be tractable for any k which is of order 1. Okay, because you're doing linear algebra on polynomially sized matrices. However, it becomes intractable for k being for high dimensional holes, okay, which is a problem that appears in TDA often. Okay, so let me tell you a little bit about the Clique and the independence complex, which are the specific complexes relevant to TDA. So these are specified by a graph. So you give us an input certain graph G, and then you're instructed to find the cliques of that graph. So that means subgraphs, complete subgraphs of G of size K, that is a K clique. And given a K clique, you construct a K simplex, and then you glue them together in some prescribed way, and then you obtain the so-called Clique complex of the original graph G. So I'll describe how this works in more detail soon. Similarly, if you have a graph, another nice thing you can do is find independent sets, which is subsets of vertices of size k, which are not connected by any edge. Okay? And it's straightforward to see that cliques of one graph are the same as the independent sets of the complement graph, where you delete all the edges where there were some, and you put edges where there weren't any. And as a consequence, the independence complex of a graph G is the same as the clique complex of the complement graph. So we can talk about the two indistinctly. And I'm going to focus mostly on dependence complexes because they're easier for me. Okay, so what is the independence complex? So let me just give you an example how it works. So suppose you're given this graph. So it has to be a simple graph, meaning that it doesn't have self-loops, and two vertices are connected by no more than one edge. There are no double edges. And then you're instructed to find all k independent sets. So for example, what are one independent sets? You just choose one vertex out of n. So you have as many independent sets as vertices. Two independent sets, you have to choose all collections of two vertices such that they're not connected by an edge. So you'll find a certain number of 2 independent sets. And in this example, the maximum independent set is a 3 independent set, and then it stops there. You cannot choose one more vertex such that they're not connected. So as I said, to each k independent set, you associate a k-dimensional simplex, and you construct a simplexer complex. So let me give you an example here. So for example, let's start with this graph, which is going to be a disconnected graph of 2 triangles, which perhaps is a kind of strange example to begin with, but they will be relevant for my purposes later. So in particular, these will become 2 qubits. So let's look for 1 independent set. So those are just the vertices. So there are 6 of them. And 2 independent sets, you have to choose 2 vertices which are not connected by an edge. So I have to choose 1 vertex from each triangle. So there are a total of 9 1 independent sets. And then you draw the simplexer complex, which has 6 zero simplices and 9 1 simplices, or edges. Okay? So in this case, it so happens that this independence complex is a graph because there were no independent sets of size 3. So it just so happens to be a graph, but don't confuse the independence complex with the original graph. In particular, if there were 3 triangles, then this would have some filled-in faces. If you have n triangles, it will be n-dimensional. Okay, so what is the homology of this complex? So let's look at it. So here, so the claim is that it has 4 one-dimensional holes, which you can see here. So this is a closed cycle, okay? So it satisfies the first condition is in the kernel of the boundary operator, and this cycle is not the boundary of any 2-dimensional simplices because there aren't any. So it's obvious. And this is the second cycle, and this is a third cycle, which is kind of this handle, and this is another cycle. So therefore, and any other cycle that you can come up with will be linear combinations of these. Okay, so this is a basis for 1-dimensional cycles in the simplexer complex. Okay, so this is how you count things. Okay, so for obvious reasons, we're going to call these, we're going to use this kind of binary notation for these 4 cycles, and we're going to call them computational cycles. And the claim is that if you have n triangles, what you obtain is something that I cannot draw, but basically it's a kind of a Swiss cheese that has an exponential number of holes in high dimension. So the Swiss cheese have dimension n, the holes will have dimension n-1, and there will be an exponential number of holes in this space. And so this is large enough to we're going to hide our Hilbert space inside this Swiss cheese for our reduction. Okay, so let's move on to part 2, which has to do with supersymmetric many-body systems. So put everything on hold that you learned about supersymmetry, about homology on pause. So in particular, I'm going to be talking to you about supersymmetric quantum mechanics. There are generalizations of this that go beyond that, but in this case, we just need so-called supersymmetric quantum mechanics. So any Hilbert space can always be decomposed into a bosonic subspace and a fermionic subspace. So you should think of this as the subspace which is generated by symmetric and antisymmetric states under exchange of particles. Now, what is a supersymmetric quantum mechanical system? It's a system for which there exists an operator called the supercharge that maps bosons to fermions and fermions to bosons. That's basically it. That's the hallmark of supersymmetry. Okay? There's some decomposition of the Hilbert space into bosonic and fermionic states, and there's an operator that maps one into the other. Now, for technical reasons that I will go into, the class of supersymmetric system will consider have the property that the supercharge squares to 0. Okay, so this follows from some constraints from super Lie algebras that I won't go into. But for those of you who know a little bit of supersymmetry, this is called an n=2 supersymmetric quantum mechanics. Now, the Hamiltonian of the system, by definition, is given by Q dagger plus Q dagger Q. So Q is a complex operator here; it's not Hermitian. And in particular, so you take this combination because now this maps bosons to bosons and fermions to fermions. And that's how the Hamiltonian usually acts. So you say that H as an operator is bosonic, but Q itself is fermionic, and 2 fermions give you a boson. Okay, so the reason why homology will enter in this particular model is because this Q squares to 0. So this will become the boundary operator. So a couple interesting properties follow directly from these definitions, which are as follows. So if you look at the spectrum of supersymmetric systems, the first thing to notice is that the spectrum is positive semi-definite. So there can be states with 0 energy or positive, but not below. Okay? And you cannot just willy-nilly kind of shift the Hamiltonian because it won't have the structure of Q dagger plus Q dagger Q. Okay, so there's a kind of preferred reference point. The second observation is the states which have positive energy are paired. Okay, so you see that for every bosonic state with a certain energy, there's a corresponding fermionic state with a certain energy. And that is because of the existence of this operator Q. So if you have a bosonic state, you act with it on Q and you obtain a fermionic state, or vice versa. All right, so states are paired, and these are called supermultiplets. However, the states which have zero energy are not paired. And let's investigate what happens if something has zero energy. If you use the formula of the Hamiltonian given by the anti-commutator of Q and Q dagger, you see that you can just rewrite this expectation value in this form. And so for this to be zero, the only way this can vanish is that both Q acting on psi and Q dagger acting on psi is zero. Okay? So that means if you have a state with zero energy, you try to act with it on Q, it won't have a partner to go into. It's just that state is annihilated. If you try to act with the Q dagger, that's also the case. So these states which have zero energy are singlets of supersymmetry, and the ones which are excited are doublets. Two different representations of supersymmetry. So Witten pointed out in his 82 paper, and this is kind of physics version of Hodge theory, that states which are annihilated by both Q and Q dagger, you can equivalently say that state is in the kernel of Q, but not in the image. So these two statements are equivalent. Okay. So this is basically saying that psi is in the kernel, meaning that it's annihilated by Q, so it has no super partner, and it's also not in the image, meaning that it's not the super partner of someone else. Okay. So that's why states which have exactly zero energy, which are the absolute ground state of supersymmetric systems, are elements of homology of the operator Q, the supercharge. Okay. So now let's look at a particular model called the Fermi-Hardcore model. The Fermi-Hardcore model is the following. So you could take the same graph for which we computed the independence complex before, and consider fermions hopping around this graph. And we're not going to allow, it's called hardcore because you're not going to allow fermions which are, you don't allow fermions to be connected by an edge. They have this kind of strong repulsive core. So they're fermions, so they cannot both be on the same vertex, but also they cannot be neighbors. And let's give some dynamics to these fermions. So the natural thing to do is you'll add some hopping term, but that hopping term has to be consistent with the hardcore condition. And in order for that to be the case, you introduce these projectors, which go to zero if any neighbors occupied. And this is where, so you could study the dynamics of the system. It's still non-trivial because of these projectors. It's not a free theory. But it will not be a supersymmetric theory. It will not connect to homology in any way. But if you add a very finely tuned potential, which is given by this, then the system becomes supersymmetric in the sense that you can write it like this, where Q squares to zero. Okay, and this is by definition a supersymmetric system. And now the claim is that this system of hardcore fermions captures the homology of the independence complex that I described before. Okay, so you can do two things. You start with a certain graph that we took as an example before. You consider fermions hopping around the system. You can compute the spectrum. You see that it has the properties of a supersymmetric spectrum. And there are 4 states which have exactly zero energy. And if you remember, when we computed the homology of this independence complex, we also found 4 one-cycles. Okay, so you have this connection that the supercharge on the left-hand side is identified with the boundary operator, and the fermion number, how many fermions there are in the state, is mapped to the dimension of the corresponding simplex. That's the basic map between the two things. Okay, so part 2 of the talk is going to review very quickly basic aspects of computational complexity. So I'm just going to go and dump here the definition of QMA₁. So let me remind you that what QMA is. QMA is the class of problems which, if in the case of a yes instance, you can efficiently verify on a quantum computer given a quantum witness W. Okay. And so if in the case of a yes instance, you input a quantum state W, in QMA you would require that the probability of accepting is higher than, say, for example, 2/3. But the difference between QMA and QMA₁ is that here you accept with probability 1. Okay, so that's the only difference between QMA and QMA₁. And there's a low probability of accepting in the case of a no instance. So it's still an open question whether QMA is equal to QMA₁. This is the case in the classical setting, but is not known in the quantum setting. So these two classes could be equal to one another. Okay, so this all depends on a particular choice of universal gate set. And a common choice of universal gate set is the Hadamard, T-gate, and a C0 gate. Now, as you'll see, for our purposes, this has some ugly square roots of 2s and some i's that are not really, they don't play nicely with topology. So we're going to change our universal gate set. And luckily, so there's another choice you can make, which is a C0 gate together with a 1 qubit gate U, as long as it is basis changing, so meaning that it creates some superposition of quantum states. This pair forms a good universal gate set. So we're going to choose this universal gate set, given by this 1 qubit gate, that we're going to call the Pythagorean gate for obvious reasons. So for this to have determinant 1, it has to be any Pythagorean triple defines such a gate. Okay, so let me remind you what quantum K-SAT is. So in quantum K-SAT, this is a canonical QMA₁ complete problem. So you're given a collection of n qubit K local projectors pi A, and you ask to decide whether there's some quantum state psi, which is annihilated by all the projectors. Okay? That will be the case of a yes instance. Or otherwise, if the expectation value of the sum of all these projectors is bounded below by 1 over poly n. Okay? This would be the case of a no instance. Promise that one of these is the case. Okay? So, for example, here on the right-hand side, the sum of all the projectors can vanish if and only if all the projectors are 0. So, okay. All right, so a theorem proven in 2006 by Bravi and later improved by these authors in 2013 is that quantum 4-SAT is QMA₁ complete. Okay. And so we're gonna reduce from this QMA₁ complete problem to show QMA hardness of our problem. So let me just remind you how that construction works. So you have a clock construction which is very similar to those of you who have seen it, to Kitaev's clock construction, which is the following. So given a QMA₁ circuit, U sub x, made out of our universal gate set C0 and the Pythagorean gate, you construct some projectors that depend on these gates, and then you construct an instance of quantum K-SAT. So in the case of yes instances, there exists a certain state, which is the history state, that is annihilated by all these projectors. Okay? And in the case of no instances, you're promised that this Hamiltonian, which is given by the sum of the projectors, is lower bounded by 1 over epsilon. So you can encode the entire circuit. So if the circuit accepts, then you are in the case of a yes instance, and there's some state, the history state, for which all the projectors vanish in it, and otherwise you can prove that there's this inverse polynomial gap. And the Hamiltonian has the following form. It has this Feynman-Kitaev form, which is very similar to Kitaev's original 5-local clock construction, except that the clock is a little more complicated. And that's just to reduce the locality from 5-local to 4-local, that the clocks are more complicated and have these 4 states. But you can see that the core of the Hamiltonian is given here. This is where the computation is being encoded. So these UT dagger are the different gates appearing in the quantum circuit. And it's easy to see that all these terms, they're all themselves projectors. So all these clock terms are projectors, and all these are projectors, meaning they square to themselves. So this is indeed an instance of quantum 4-SAT. Okay, so here's a table that is summarizing all the data that you need in this clock construction of quantum 4-SAT, meaning these are all the projectors that appear, and these are the corresponding states which are rejected by the projectors. Okay, so in the absence of any gates, any n-bit string is accepted in the QMA₁ protocol. But as soon as you start putting in some gates, some states will be rejected, and these are the states that are rejected, corresponding to all these different gates. Okay, so this is going to be our progress card later. We have to fill this card in. And the goal here is to encode all this data into the Swiss cheese that I showed you before, okay? To show that the Swiss cheese with all these holes it carries as much computation power as a QMA₁ circuit. Okay, so that brings us to the final part of the talk, which is the proof of our main theorem. Okay, so the main proof idea is the following. So as I said, we're going to take as a Hilbert space this space which has an exponential number of holes, 2 to the n at dimension n-1. And what we're going to do is we're going to take all the projectors from quantum foresat, and for every projector, we're going to fill in one of these holes. Okay, so we start with the first projector, fill in one hole in a way I'll describe, second hole, a third hole, and so on. And such that when we're done, the number of remaining holes is in one-to-one correspondence with the number of accepting strings to the QMA₁ protocol. So for every rejecting string, I fill in a hole. So at the end, when I'm done with getting rid of all the rejected strings, I'll be left with a certain number of holes. Okay, so these are the holes that we need to fill, and we're going to go systematically through them. Okay, so what's the first step? The first step is creating the Hilbert space. So as I said before, this is going to be given by a collection of n disconnected triangles, and now we can do two things. We can construct the independence complex, which I already told you has this number of holes. Another thing we can do is to construct the fermionic hardcore model on this graph. Okay? The same is that these two are equivalent by Witten's general isomorphism. And indeed, if you look at the spectrum of the Hamiltonian, supersymmetric Hamiltonian of the system, you'll see that there are indeed 2 to the n number of states with exactly 0 energy. These correspond to the 2 to the n elements of homology. Whether the states are bosonic or fermionic depends on whether n is even or odd. So in this case, I took it to be even. So all the ground states, these are called supersymmetric ground states, those which have 0 energy. There are 2 to the n of them, and they're all bosonic. And then there's 3 to the n, or the 3 to the n states above it. Okay? And they're all paired. You can check. Okay, so here's the idea. As we start filling in the holes in this cheese, we'll have to start pulling out. That means that elements are being taken away outside of homology. Okay? So the number of holes is decreasing, so the dimension of the homology space is being reduced. And correspondingly on the left, some states which have 0 energy should be lifted up. Okay? But the problem is that we cannot just willy-nilly uplift, like pull a state out of the vacuum, because it will be inconsistent with supersymmetry. If we want to pull out one state, it has to be paired up with another state. And because there's no other state, then you cannot do that. So these bosonic states are kind of trapped in the, topologically trapped in the E equals 0 ground space. Okay, so we'll have to find a way around that. So how are we going to do this? Well, let's start with an example. So let's start with the clock. So the clock rejects strings which are the form. So here I'm just focusing on how it acts non-trivially on 2 qubits. So it projects onto all the states orthogonal to 0, 0. Okay. So because this projector in the clock construction rejects the string 0, 0, that means that when I identify in my 2-qubit system the cycle that I call 0, 0, I want to eliminate this state from homology. Okay, so I don't want this state to be a hole anymore. So this is a hole, and I want to get rid of it. So how do you get rid of it? You fill in the face. That's one way to get rid of it. Because now this cycle that is surrounding the space, now it can be contracted. Okay? So I cannot just fill I cannot declare that the face is filled, because I'm only allowed to use triangles and higher dimensional generalizations of triangles. So I cannot just say that the square is filled in. I need to triangulate the square. Okay? So I add this extra vertex, and we connect it in that way, and we fill in those faces. So now you see that from the 4 elements, elements of the first homology, we've deleted one of them. So we've accomplished what we wanted. Now what I can do is I can reverse engineer what this procedure is doing at the level of the original graph. And what that is doing is introducing an additional vertex that connects in this way to these triangles. In other words, when we started, we had a tensor, we had a Hilbert space, which was a tensor product of triangles, and they all had their own energy levels, and we had 2 to the n 0 energy levels. And now by connecting them, we are lifting certain states. Okay, by interactions. So now the fermions are allowed to hop from one triangle to another, and that lifts certain energy states. And this is engineered in such a way that the only state that is lifted is 0, 0. So indeed, what you see what happens is that introducing this extra mediator vertex introduces a number of states, okay? And in particular, there's one fermionic state, which is all by itself, which is basically just one fermion sitting here in the mediator, which is connected, sorry, that's not the state. I said it correctly, correct myself. So there's a bunch of states which are paired up, but there's one state which is left alone, but it pairs up exactly with the state that you're trying to lift, and it has exactly the right energy. So things match, and there are just 3 states left in the ground state. Okay, so that's a baby example, and you can repeat it for all these different variations here. So these are just relabelings, and then higher dimensional things are very similar. Okay? So what is more complicated is how to deal with these entangled states. So that appears when you consider, for example, the C0 gate. So here's again an example. So we consider this 2-qubit system, and now we identify the cycle 0, 0, -1, 1. So imagine you want to lift this state, an entangled state. So what I've drawn here is the exact same simplicial complex that I drew before, just kind of drawn differently to highlight this particular cycle here, 0, 0, -1, 1. So you can imagine taking the strings that I had before lying on the table, you lift it up and you put it back on with this different shape. So you identify this cycle, and I want to fill it in, and that's the way to fill it in. So here you have to use a minimum of 3 vertices for reasons I won't go into. Okay, but that's how you triangulate the space, and then you can reverse engineer this graph, and so you see what you're doing is the original 2 qubits are being connected in this way, such that you lift in precisely the state 0, 0, -1, 1, but not any other. And the state that you lift is precisely matching an additional state that you added. So in total, you can count how many states you've added. You added a total of 37 new states by adding these extra vertices. 36 of them are paired in 18 plus 18, and one of them is left by itself, which pairs up with the one that you're pulling out of the vacuum. So a comment is that the more entanglement the state you want to pull out of the vacuum has, the more complicated that triangulation of the space. So this will come to really a kind of extreme example soon. Okay, so let's go back to this progress card. So what have we done? We have managed to understand how to lift all the states which are denoted there in green. Okay, so if you see, for example, the terms appearing here, these involve tensor products of this lifting this entangled state and some other classical state. So I haven't told you how to take tensor products, but that's pretty easy. So I'm going to skip it. All right, so let's consider the case of 3 qubits. So if you have a 3-qubit projector, if you have a projector that lifts this state 0, 0, 0, which appears, for example, at the clock, if you look at the table, now you have a 2-dimensional surface. Okay? So you have a 2-dimensional surface, and you want to make this the hole being surrounded by the surface to no longer be a hole, which means that you have to fill it in with solid tetrahedra. Okay? So you have to get a bunch of solid tetrahedra and glue them in the inside of this kind of capsule so that the hole disappears. So that can be done. It's not very difficult. But then again, the fun comes when you have to consider entangled states. So in entangled states, you can think of the state 0, 0, 0, -1, 1, 1 as gluing 2 of these capsules with opposite orientations, and then the phase along which they're being glued cancels out. Okay, and you obtain just one space, which is isomorphic to S2, homomorphic to S2. Okay, so you build this thing, you fill it in with tetrahedra, and then what you obtain is you reverse engineer the graph that would have lifted that state, and you obtain this. So what you can see is that you're adding 189 states to the spectrum. 188 of them are paired, and one of them is unpaired and pairs precisely with the one you lifted, and this is how you have to connect the 3 qubits. Okay? And this is actually the minimal way of doing this. Okay, so with this we complete all our C0 holes. Okay? And actually the only one that remains is this Pythagorean gate. Okay, so here this is a little more complicated, and this is where kind of the really technically challenging part of the project was, which was to understand how to lift these Pythagorean gadgets. And they're more complicated because the states that you have to lift have this form. Okay, so there's the sum of 3 terms, but not only the sum of 3 terms, but actually each term appears an integer number of times. So this is where you see that the Hadamard gate wouldn't have been good, because you would have some square roots of 2 there. And the basic idea how we're going to lift this state is the following. So each one of these is a computational cycle, and we interpret the state as being the linear combination of 5 times the first cycle, 4 times the second cycle, and 3 times the third cycle with orientations, and you want to glue them all together into one single cycle, which is the Pythagorean cycle. And yeah, as I said, if we had square roots of 2, we wouldn't know how to do this. Now, so we have these 3 computational cycles. We want to glue them into one cycle, and here we have to understand how to do this. And so we developed this tool that we call simplicial surgery, which amounts to you take one of these computational cycles, you check which are the common edges with the other cycles you want to glue, you cut a slit along the simplex, and then you glue them very carefully to make sure that you obtain the full cycle. So each of these different computational cycles you're adding needs its own surgical procedure, let's say. And then you paste them all together and you make this kind of Frankenstein of different 2-dimensional cycles, and they all have to be glued very carefully together so the topology of this whole thing is an S2. Now, once you have that object, now you can fill in it with tetrahedra, so you fill in the hole which is surrounded by that cycle, and you can reverse engineer the graph. So let me remind you that before, for C0 gate, for example, the 2-qubit and the 3-qubit gadgets were like this, but so you start observing this and you see like there's a repeating pattern, and you're pretty confident that you can guess what the next one is, and indeed you get exactly what you would expect for the Pythagorean gadget. So here there are 3 triangles. This is just a 3-qubit gate. So there are 3 triangles, and everything else are just crazy connections between these 3 triangles. And if you're wondering, this is not a complete graph. Okay? So it has some structure that you can see here and here and here. So 1, 2, 3 is one triangle, 4, 5, 6, 7, 8, 9. It's another triangle. Okay, so yeah, you get this crazy mandala as an answer, and so you need to check, a sanity check is that this is actually correct, that you didn't screw up anywhere. So to verify this, what is it that we need to verify? So we added thousands of states into the spectrum. All of them should be paired except for one, that is being paired with a Pythagorean gate, the state that we're pulling out of the vacuum. And we should not pull anything else out of the vacuum, otherwise we're filling in 2 holes. So that's what we need to check. So we need to check that the only element of homology in this crazy construction is given by this. The problem is not an NP, so it's hard to check. And indeed, even if your programming skills are better than ours, it still took us 20 hours and 40 minutes in Mathematica to run it, but in the end you get yes. So this is the only element that you pull out of the vacuum, okay, and no others. So we claim success, and that was the end of our proof, basically. So if you put all these elements together, you can map this quantum circuit and accepting witnesses to this quantum circuit to this very classical problem, okay, of whether, so this quantum circuit has an accepting witness if and only if this has a hole. Okay? Okay, so our main theorem follows from there, and the whole construction is by design done in a parsimonious way, meaning that the number of accepting witnesses is equal to the number of holes. So the complexity of the problem, the complexity of the counting version of the problem also follows from this, not only the decision version. Okay, so with that, I'm gonna tell you about the problems that remain open. So obvious problem that remains open is containment. Okay. So here we've provided a lower bound for the complexity of this problem, which is QMA₁, better than what was previously known to be NP. But if you really want to fully understand the complexity of the problem, you should be able to put an upper bound. And that is not an easy problem because that depends on the spectral gap of the combinatorial Laplacian of these simplicial complexes, which in physics jargon would be the supersymmetric Hamiltonian. So we need to understand the gap of the supersymmetric Hamiltonian. Now, we think that we can nonetheless have control over this, and there are 2 cases that one has to consider. The first case in which the promise gap for the supersymmetric Hamiltonian is inverse exponential. When it's inverse exponential, in fact, the expectation, although this still has to be proven rigorously, and there are a couple subtle points, is that if the gap is inverse exponential, which is generically the case on a simplicial complex, the problem, in fact, becomes p-space complete. Okay? However, if you impose, so you can define a promise version of Clique homology in which you're given the promise that the gap for the combinatorial Laplacian or the supersymmetric Hamiltonian is inverse polynomial. So with this promise, the expectation is that this problem will be contained inside QMA, basically just by phase estimation. You need to find the lowest energy eigenstate. So this is work in progress with Tamara, with Robbie King, who's an excellent student at Caltech, and we believe we have a handle on this, but it's still pretty much work in progress. All right, so zooming out a little bit, so there are more, so homology comes in many flavors. It's not just clique homology. There's path homology, which has applications to neural networks. There's digital homology, which has applications to image recognition, and countless more examples of homology. And all these should correspond to different supersymmetric systems. They should all be fermionic systems, many-body systems, not too different from like the ones you encounter in chemistry, quantum chemistry. And if you take the, again, this kind of intersection, so this should be a way to identify problems with potential quantum advantage. With interesting practical applications. So zooming out even a little more, there's a larger problem here, which is looking for problems with quantum advantage from using kind of the lens of mathematical physics. Okay, so but what I mean by quantum advantage is identifying problems which are BQP complete or DQC1 complete, so they cannot be easily dequantized. And here there are two natural settings. So the first is a generalization of, so it's not only supersymmetric Hamiltonians that have rich structures. There are many other Hamiltonians that appear in the mathematical physics literature. They have lots of connections to number theory and algebraic topology and so on. And so these systems, which are intrinsically quantum mechanical, should give you, hopefully, that's the hope, should kind of indicate places where you can look for interesting computational problems which are intrinsically quantum mechanical. So algebraic topology is an obvious place to look at. This includes the homology problem, but goes beyond that. But also problems in algebraic geometry, which is also kind of a whole unexplored area of intersection. So with that, I want to leave you, and I hope that this conversation continues for the rest of the week, and I'm looking forward to all of your talks and discussions with you.
Great, so thank you very much for the absolutely lovely talk. Questions? I'm told there's a box that will get thrown around. Oh, in this case, I can give it, I guess, yeah? Sorry.
Hi, thanks for an interesting talk. So you're saying that at least one type of homology is QMA₁-hard. Since you can think about error-correcting codes in some language of homology, is there anything you can say about the complexity of quantum codes that might come from these this new approach?
I wondered the same thing, and we wondered about this together with Nicholas Broekman. I don't know if he's here in the audience, but he's the expert, and so we couldn't find any obvious connection, a way to think about it, but I think we both have the nagging feeling that this should be something there. So happy to discuss. I don't have anything to say intelligent at the moment.
Hi, thank you so much for that talk. I was wondering if you could help me contextualize what else is known about these kinds of surprising problems that end up being, QMA₁-hard or something similar. For example, with NP hardness, almost every problem seems to be, in a way NP-hard, but this is a surprising thing because it's a problem that we don't think of as being quantum mechanical, and then you find this reduction. So you talked about the larger program of finding such things in mathematical physics literature, but could you contextualize this result, what was known before, and how surprising was this as one of the first things known to be?
Well, so yeah, that's a good question. So another example to this, which is very, very similar, very analogous, is the Jones polynomial story. Right? So that connection also comes through, if you want, there's a physical system behind the fact that the Jones polynomial is quantum mechanical, basically. And that's because it amounts to computing a certain partition function of a quantum mechanical system. So I think that is one example. To the best of my knowledge, kind of the second example will be these supersymmetric systems whose partition functions are also computing certain topological quantities. And these are the two examples that I know in this vein, but I think there should be many more.
Thank you so much.
I think there are questions on that side too. We should switch.
Hi, thanks for the talk. So When I know homology has free components and torsion components, and we only talked about the free components here. I'm curious if there's an analogous quantum mechanical interpretation for the torsion component of homology.
Yeah, that's a good question. So torsion appears only so torsion doesn't appear here because we're working with complex coefficients. So torsion is not seen, and homology groups are completely specified by Betty numbers. It is not natural to impose the coefficients to work with integer coefficients, which is where you would see torsion in the context of quantum mechanics. But it will be interesting to think why, physically what that could mean to constrain the amplitudes to be integers or rationals.
Great. We can take, I think, one more question.
Why does the proof is QMA₁-hard instead of just QMA₁-hard, and why doesn't this reduction work for just QMA₁-hard, basically?
Yes, so it's the same reason why quantum foresight is not so obviously QMA₁-hard. So it's because for homology, you want to know if the energy of the ground state is exactly 0 or above 0. Even if it's exponentially close to 0, you will not count that as an element of homology. It has to be exact. It's either 0 or non-zero. And if this dichotomy between 0 and non-zero that appears in quantum foresight, that makes it QMA₁ complete. So the perfect completeness, the fact that you accept 100% of the times in the case of yes instances, translates to the promise being either exactly 0 energy or above that. So in homology is the same situation. So you may wonder if the problem's inside QMA₁, but that is not so easy to show. But it's definitely inside QMA with a promise.
Yeah, I'm curious about how important is the choice of the Pythagorean gate in QMA₁. So another way I've previously seen QMA₁ defined is that the uniform circuit constructor can output any algebraic description of gates, and so could you also reduce QMA₁ definition like that to this homology problem?
I'm not sure I understand the question. Are you asking if we can use a different gate set?
Yeah, right. So, and yeah, for example, a different gate, or if you allow sort of any compact description algebraic number gate.
Yeah, so this construction, it's not obvious to us how this construction will go through with some arbitrary universal gate set, right? Because of the reason that I mentioned. Maybe there's ways around it, but we don't know. But the point about QMA₁ is it's also, it's gate set dependent, right? Its definition. So, yeah, this reduction only works for integer coefficients. So, yeah, but
Right, thanks.
It's an open problem. Yeah.
We're already bending the rules a bit. Is that okay? Can we take one or two more questions? There's still more. Can an organizer yell at me? It's okay? Yeah, good. So there was one here.
Hello, thank you for your talk. You said that homology is what you explain quantum computation and quantum the complexity of it. Yeah. But you in your previous slides you say also it is behind neural networks.
It's what, sorry?
Neural networks and neural networks.
Oh, path homology, yes.
So how do you link between, how can it be behind neural networks and also quantum circuits or quantum complexity?
Okay, I'm not sure I fully understand the question, but so if I understand it correctly, you're asking how can something quantum be behind neural networks? Right. So you can ask the same question about simplicial homology, right? It's also something entirely classical, right? This block of cheese, whether it has a hole or not. There's no superposition, nothing there going on, nothing quantum. But so the connection to quantum goes through this special class of Hamiltonians, of supersymmetric Hamiltonians. So they don't look on the face of it apparently quantum mechanical, but they are intrinsically so. In the sense, and one should be careful here, that it depends on this gap also, right? Because if you allow this gap to be inverse exponential, you can go all the way to p space, and then you would say, well, it's a classical problem in that sense. It's a classical complexity class. But what the lens of quantum mechanics tells you is what it should be the right promise to impose so they can bring their problem down from p space down to exactly a quantum mechanical class, QMA, QMA₁, or BQP. So in the case of neural networks, that will be also very surprising, but I suspect that the same story holds there as well.
You mentioned the connection to the Jones polynomial.
Yeah.
So
You should
maybe
know
it was
about that.
hidden. Maybe it was hidden here, but is there a strong relation to representation theory, like here? And also, do you know of a problem related to the Jones polynomial that is QMA₁-hard in a similar way, or that is QMA-like and not BQP-like?
You mean a QMA₁-hard version of the Jones polynomial? I don't know. Good question.
And representation theory.
Yeah. Sorry?
And the question about representation theory?
Yeah, what's the question about representation here?
Well, in the Jones polynomial case, there is a very strong relation to representation theory.
Yes.
The proof that of the Jones polynomial being BQP complete goes through representation theory.
Yes.
I was looking for representation theory here. Is there any hint of that?
Not in Clique homology, but I cannot. Yeah, maybe in other settings of homology, it is quite possible. There are a number of problems which don't seem homological, which can be formulated in terms of homology. Perhaps even some problems in representation theory. So, for example, there's a problem in group theory, finding fixed points of the action of groups. That can be formulated as a problem in homology. Problems in number theory, for example, finding Pythagorean triples, which has been solved for thousands of years, but you can formulate it as a homological problem. So perhaps there's a way to formulate some problem representation theory in terms of homology, but I'm not aware of any.
Good. So already over time in the very first session, so you guys can kick my ass outside. Before we close, is Tamara here, the other co-author?
Yes.
Raise your hand, stand up. People see your face too. There she is. Okay, so congratulations to both of you on this excellent work. Yeah.